5, 4, 3, 2, 1. You know that countdown? That's the exact number of marks standing between your current grade and the ultimate A-star boundary in your Cambridge IGCSE Additional Mathematics exam. Every single mark matters, right? And losing them on easily avoidable differentiation errors is a massive hit to your overall score. Well, today, we're eliminating those errors entirely and hacking the exam to secure your target grade.
Okay, let's dive into this. Think about the immense, incredibly complex orbit of the planet Saturn. Now compare that to a simple, everyday red apple. So what do planetary orbits and a falling apple actually have in common with passing your upcoming math exam? I know, it sounds like a trick question, but the mathematical connection between these two objects is the very foundation of the tool you absolutely need to master today.
That connection was originally made by none other than Isaac Newton. You've probably heard his famous quote, right? "If I've seen further than others, it is by standing upon the shoulders of giants." But here's the crazy part. In his early years, the mathematics of the time simply wasn't advanced enough to calculate the elliptical orbits of the planets. To solve this exact puzzle, he literally had to invent calculus. And this historical toolset, specifically differentiation, is the absolute best weapon you have to hack the Cambridge 0606 exam. We're going to use Newton's tools to secure those top-tier marks. Part 1. The Gradient Function Arsenal. All right, let's transition into equipping you with the foundational mathematical weapons required to beat those grade boundaries. Before we tackle the really complex, high-mark exam questions, we need to make sure your basic arsenal is fully loaded and ready to deploy. Differentiating basic powers of x is one thing, sure, but you also need to know these functions intuitively, like the back of your hand. Sine x becomes cosine x. Cosine x transforms into negative sine x. Tangent x becomes secant squared x. E to the power of x beautifully remains e to the power of x, and the natural log of x, that becomes 1 over x. So the crucial point is, when you're differentiating any of these trigonometric functions, the angle absolutely must be in radians, no exceptions. If you leave your calculator in degrees during the exam, you will lose those marks instantly, no matter how perfect your algebra is. Poof, gone. Moving beyond the standard functions, your exam is practically guaranteed to throw composite scenarios at you. And that's exactly where these 3 essential rules come in. First up, the product rule. You use this when your function is the product of 2 distinct algebraic expressions. Second, the quotient rule. This is your specific tool when one function is divided by another. And finally, the chain rule, reserved for composite functions or, a function of a function. It really helps to think of these rules cleanly separated. Don't just view them as abstract formulas, but as specific, purpose-built tools designed to dismantle specific algebraic obstacles the examiner puts in your way. Now, I want you to pay close attention to this next part. In a moment, I'll look at the examiner clue that changes an answer completely, a sneaky little trap that catches out thousands of students every single year. But first, you need the framework to actually spot it. So let's build that framework right now. Part 2. Mastering stationary points. Okay, we're escalating the stakes a bit here. Knowing how to differentiate, that's just step 1. The real high-value marks are found when we apply this to a mathematical scenario. Specifically, we need to know exactly what happens when our gradient function hits exactly 0. By definition, a stationary point is a specific coordinate on a curve where the gradient is exactly 0. Basically, it means the tangent line drawn right at that point is perfectly horizontal. Now, in your exam, this can manifest in 3 distinct ways. It could be a maximum turning point, where the curve changes direction from a positive to a negative gradient. It could be a minimum turning point, swapping from negative to positive. Or it could be a stationary point of inflection, where the curve flattens out and twists, but doesn't actually turn back on itself. Once you've actually found a stationary point, you have to prove to the examiner exactly what type of point it is. Now, what's really interesting about this slide is this foolproof method to classify these points quickly. It's called the second derivative test. Step 1, you differentiate your gradient function a second time to get d2y over dx squared. Step 2, substitute your x-coordinate into this new function. If the result is less than 0, boom, you've mathematically proven it's a maximum point. If it's greater than 0, it's a minimum point. Utilizing this completely avoids the time-consuming errors so many students make when they try manually checking gradients on either side of the coordinate. Part 3. The top band exam framework. Let's resolve that open loop from earlier. How do we take all these abstract tools, the product rules, the standard derivatives, the stationary points, and turn them into a concrete, reliable strategy for conquering these exact Cambridge IGCSE questions? Well, here is the high-retention exam methodology you need to lock in right now. 1. Read the problem carefully, identifying exactly what mathematical concept is being tested. 2. Select the method. Is it asking for the quotient rule or the chain rule? 3. Show your steps explicitly. Please do not try to do complex algebra in your head. 4. Check your accuracy as you go. And 5. Finalize the answer cleanly. Let's look at a really concrete example of what happens when you decide to skip step 3. And this brilliantly illustrates the critical difference between an average exam paper and a top band exam paper. Take a look at the flawed student answer. They jump straight into applying the quotient rule formula in their head. Now, because the quotient rule has a minus sign built right into the numerator, skipping the explicit definition of u and v almost always leads to a fatal sign error. It happens all the time. But look at the top band answer. They explicitly write out u, v, the derivative of u, and the derivative of v right there on the page before ever touching the main formula. This forces accuracy. This is exactly where those final grade bounding marks are lost and gained. Part 4. Spotting Common Examiner Traps. We are now entering the final boss stage of this explainer. Examiners absolutely love to use specific tricks to trip you up, especially when it comes to combining differentiation with practical applications like connected rates of change or small increments. So I want you to pause and predict right now. If x increases from 3 to 3.001, how do you find the approximate corresponding change in y? Actually, most students will fall right into the examiner's trap here. They'll try to manually plug 3.001 back into the original complex equation, wasting precious exam time and honestly likely making a calculator error along the way. So what is the correct mathematical solution? Let's move to and see how this builds directly on our gradient function. This is the small increment formula. The small change in y, represented by delta y, is approximately equal to the gradient of the curve, dy by dx, multiplied by the small change in x, delta x. So if x increases by a tiny fraction, like 0.001, you do not recalculate everything. You simply evaluate your derivative at x equals 3 and multiply that gradient by 0.001. It is an incredibly fast, highly accurate shortcut that connects the gradient function directly to the approximate change. It's a real game changer. So we've covered the differentiation hacks, mastering stationary points, and bypassing those sneaky small increment traps to secure your foundational marks. But what is the exact evaluation framework required to secure those final high-tier marks when the exam questions become massively complex and multi-layered? You know, when the whole shebang is on the line. You need to know how to structure your final evaluation flawlessly. Make sure you jump straight into our next explainer on the top band evaluation framework right now. It is absolutely your mandatory next step to exam mastery. See you there.